Okay. How was your lunch? Yes? Good lunch? There's like this really light projectors here, so I cannot see you, but I can hear you. So hi, my name is Katerina. I am Ukrainian and I live in Estonia right now. I work at Veriv. We are here. You probably noticed our booth. We are the ones with the holographic stickers and fidget cubes. And today I want to talk about memory management. I know that this is a little bit unusual topic for a lightning talk, but I was once really fascinated by the question of eventually everything that we do on our computer becomes a bunch of zeros and ones, and how the code that we actually write in JavaScript goes into that direction, and what are the things that are happening in between. So I kind of went on down the rabbit hole trying to understand how it works through V8 references, garbage collection, optimization, and I really found this interesting and I want to share it with you. So I want to invite you to the same rabbit hole and I will show you around. And with this talk, I want to give like a high level overview of memory management, kind of like crash course in 15 minutes or less. But first, let's start with those zeros and ones and understand how computers represent and store information. So 0 or 1 represents the smallest fraction of information there is. It's like on and off switch, true or false. In the computer's hardware, it determines whether there is current, charge or not, and it is called 1 bit of information. And using this binary, we can represent almost any information there is. Small numbers, bigger numbers, characters, emoji, and even the answer to the ultimate question of life, universe, and everything. But how do computers store information? There are different ways that they do it that store those zeros and ones in unique ways. But when we are talking the memory that our JavaScript applications use, it is usually RAM or random access memory. This is like a working memory that CPU uses when running our application. So let's see how that works on a high level. First of all, we need some kind of box that can store 0 or 1. And it is usually implemented under the hood on the hardware level with like a chain of transistors or a combination of transistor and capacitor that can actually hold charge and we are able to read and write through it. But of course, with one cell, we can't really achieve much. So we can put all of those cells in this kind of grid, right? And then we need a way for us to access like every specific box in there. And for that, we can use an address. An address is like kind of like this street and house address in real life. So we can take the first part of the address here and take the column and then the row by the second part. And then on the intersection will be the memory cell that we are interested in that actually stores that 1 bit of information. So yay, we just read 1 bit of information. But it's actually not a lot. It's kind of almost nothing in the modern computing. So we need to read more bits of information at once. And for that, we can arrange these matrices into an array and then access them all at once with the same address. And then we can take those cells together and basically read more bits at once. And right now here we have 8 bits, so we just read 1 byte of information. And to simplify and move up a level of abstraction a little bit, we can think of it of an address and then the data that is being stored in it. And in a decimal form, to simplify as well, it will be a number 88. And we can represent the whole memory as this kind of continuous array of addresses and the data that is being stored in there. Right now, we've been using 8-bit addresses, which means that in total, we can store only 256 bytes. And in modern computing, this is not a lot. This is less than your average meme. So modern computers actually operate not on 8-bit, but usually on 64-bit architecture, which means that addresses get really, really long. And usually you look something like this. And we use hexadecimal format to represent those addresses in memory. And when we are trying to store something, often it cannot really fit within 1 byte. So it occupies this kind of whole segment of memory. And we can say that then this A, for example, here is pointing to an address that is in the beginning of the segment that it occupies. And in the languages like C and C++, you actually have freedom to use like allocate and free, and you have access to those pointers. You can read and see them yourself. But when you're writing JavaScript, we don't really need to think about memory that much. which is actually a good thing. JavaScript is a pretty high-level language, and all of the memory management is done for us automatically by a JavaScript engine. In this talk, I will be talking and focusing mainly on V8, but other engines implement similar features within them as well. So let's take this small piece of code that just defines an object and see how V8 stores it in the memory. So let's kind of follow this white rabbit into the rabbit hole, following my Alice in Wonderland analogy. So first of all, there are two types of memory that V8 uses. This is stack and heap memory. And this is something not very unique to V8 specifically. These are just common computing terms that are used by other languages as well. And stack is a region of memory that allocates kind of local context when executing your code. And heap is a much larger region that stores everything that is allocated dynamically, say your objects, functions, arrays, and so on. So in this case, if we take that object, we can put it somewhere within the heap. And then it also has a value of color, right, which is a string inside. And it wouldn't be stored within the object itself, but actually will become a pointer that is pointing to an address where that string is stored. And most of the primitive values in JavaScript are actually allocated on the heap, except for small integers or SMI in V8 terms. And then when our code is actually getting executed on the stack, we will have a reference to this heap object that is defined. And under the hood, V8 uses this heap object of superclass, and all of the objects and strings and everything is kind of like subclasses under it, and creates the hidden classes. There is so much going on. And while our project, our code is actually being run, we allocate more and more objects into the heap. And if we get back a little bit to the whole kind of like a memory array analogy, we can zoom out and see that basically heap and stack are located on different sides of the memory segment that is dedicated to our application, and they are growing towards each other into the free space. And of course, when our JavaScript application is run, it's not that all of the RAM out there is accessible to us. We share it with all of the other applications that are being run on the computer, but also all of the different like tabs and browser plugins in the browser. So this can give a little bit more insight of why Chrome can be sometimes so memory hungry. Yeah. I see you love GIFs, yeah? But let's get back to our code as well. So we already have this object here. Let's say we create another variable. In this case, will be foo, which is a string. So we see that this is actually the same string, right? This is the same string y. How the memory will be allocated? Will then we create another segment inside the memory with the same string? Actually, no. V8 uses a thing that is called the string interlining. And basically, both of the strings will become like pointers to the same memory space that where it is stored. And that's what most of the all of the variables in JavaScript are. They are pointers. And we can go a little bit further and reassign foo's value, for example, to like another string, ping, for example, here. What will happen then, right? We'll allocate another space within our memory to store the string, and then the foo will right now be pointing to another heap object. And to simplify this a little bit and zoom out, we can imagine it as this kind of mental model, right? Where our JavaScript variables are wires that are connecting to values stored elsewhere. And when we are changing, we are just like moving those wires around to the new value. But let's talk a little bit about objects as well, how objects work under the hood. So we have this object here right now. There's two properties, and we can assign it to another object, another rabbit here, for example. And then when we are modifying that object, actually the value of the original object will be changed as well. So when we are doing modification here, it is actually changing in the original object as well. And this is called modification by reference. And often when we are writing our React code, it can also backfire to us. So for example, if you have an object that is coming to you in props and you're modifying it by reference, it will be changing in all of the parent components out there or even in your Redux store. And this is why sometimes it can be actually dangerous if we are not knowing what we are doing. And it actually works with all of the nested objects as well. So if we, inside the rabbit, we would have another object and we modify that one by reference, it still holds its own reference within the heap as well. But let's look why that actually happens on the heap example, right? So we already know how to allocate simple objects, so we did that. When we create a new object here, this is actually a pointer that is pointing to the same heap object inside the heap. And when we are making the change, it is being changed in the original one, and then the both of the references, they still keep pointing there. And if we zoom out again on our model, this is what happens. And now we can see that this Niven string, right? This is something that we don't really need anymore, right? We overridden it with another string. And this actually kind of becomes garbage. We don't really need it anymore. So let's understand that how this memory is actually freed, because this string was already occupied some kind of memory, and after our program runs, we need to free it somehow as well. But before we go into how garbage collection happens, let's understand how we can actually understand whether something is alive or not, or whether it needs to be actually garbage collected. We can represent all of the objects that we create as this kind of chain of references that go from the root. And as our programs run, some of those references stop existing, as it was in the example that we covered before. And then they become not really reachable from the root. And then these objects are considered kind of like dead, right? And then they can be garbage collected. But when the garbage collection happens, if we imagine this kind of like RAM memory array that we talked before, and just take away those values from there, our memory becomes fragmented, right? There's a lot of those small little spaces out there, and it becomes really hard to allocate anything new in the memory because it needs to fit into those small chunks. And this is where also after allocation it's important to compact the memory back so that there is more free space available for us when we are allocating new things. But let's talk about heap and how V8 actually manages garbage collection. The whole heap is split mainly into two main generations, young generation and old generation. Let's talk young generation first. This is the one where when we create objects, they actually get allocated first. It is very small and just only for the new objects when we create them, and usually in the size between 1 to 8 megabytes. And in itself, it is actually split into two different spaces that are equal in size. And when we create different objects, as our program runs, we create them and they are allocated there. But then at some point, another object, we need to allocate memory for it, but then there's just not enough. And that's where garbage collection cycle kicks in. It stops the execution completely, and that's why this called kind of stop the world. In the latest version, it actually kind of splits some work, but then there's still execution stopped. So in some cases, if you notice, for example, like a lag in your animation, could be that the garbage collection cycle is actually running right now. And after that, we need to identify which objects are alive. So basically, it traverses through all of the references from the root and understand which ones are still needed, and then copies them into the to space. And that's why it's actually called from and to space, because from to, right? So now everything we had before can be cleared, but we cannot really do that because we still have those references. So we need to reappoint those references to the new locations in the memory, and then everything can be safely removed. After that, they just swap places, and now to space become from space, and then we can continue execution, and garbage collection cycle finishes, and we can allocate our new object into the memory. This algorithm that I just covered right now that is used for the young generation is called the scavenger. And you can notice it is pretty memory hungry. Every time we need twice the needed memory to facilitate its work, which is okay for small amounts of space, but it's not really sustainable for everything. And that's why the old generation exists. The whole young-old generation dynamic is based on the generational hypothesis, meaning that most of the objects die young. And you can notice that when you're running your code, you often create like a small object that you don't really need after the function's execution. And that's what this hypothesis is based on. And basically, most of the objects are allocated and then immediately become unreachable. So when in young generation, we already fill in our heap and garbage collection cycle runs, all of the objects that they survived the garbage collection cycle, they are kind of marked as being in this intermediate step. And then after it fills up again and the new garbage collection cycle runs, we actually take those objects that were marked before, if they're still alive, and then they are not staying in the young generation, but instead they are moved to the old generation now. They are kind of promoted. Now let's talk about this old generation. So basically most of the heap is actually old generation. It's way bigger, and it often grows when you grow your application. And when our program runs, V8 kind of smartly tries to understand when and how the garbage collection cycle needs to kick in. For example, by how often you allocate new memory and how do you use it. And for that generation, we cannot use this algorithm anymore as we use the scavenger, for example, for the young generation. We need to use something a little bit more complex, and therefore the algorithm of mark and sweep is used. And it basically traverses through all of the objects by the reference chain from the root and marks the ones that are alive, and then it can safely remove and sweep away all of the objects that are not needed anymore. And then after that, there's actually quite a lot that actually goes into the hood, where we need to compact the memory again and it's split into different pages to make sure that we don't have fragmented memory and it's easy to allocate things in the future. So we talked a little bit about how our code in JavaScript gets then moved into V8, how it is all allocated in stack and heap, and then how garbage collection cycle works, how then it goes all into the RAM and then becomes a bunch of zeros and ones. And there's actually way more things that happen under the hood, and they did not fit into 15 minutes in this talk about heap objects and hidden classes and how all of the references get reappointed, how do we understand what kind of size we need to allocate. And I definitely don't know everything myself, but I still hope that you enjoyed this dive into memory management, and you can find me on this social media. And if you want to discuss and chat about memory or like React stuff or anything else, you can find me at Varif booth afterwards. And yeah, thank you.